Today we're going to spend some time on our favorite word problems. And within our word problems, there's some vocabulary that we're going to want to know. And we've done these throughout the semester, but we'll review them just a little bit. Anytime that we see the word rate, that should, in our mind, tell us derivative. Velocity, again, derivative. How fast means derivative. If I ask you how many, that's going to be, or how much, the original function. So let's go ahead and look at a couple of examples. I just have two for you today. In example 1, we're going to give you the velocity of a car given by the function f of t equals 2t plus 1. And this is going to work for any time between 0 and 20 in feet per second. So again, we see that word velocity and we see feet per second. That should, in our mind, tell us that we're working with a derivative. If the car is 20 feet from its starting point after 3 seconds, can we find the position at any point in time? In this case, t equals 10. And we can. How are we going to do that? Well, if I give you the velocity and I want to know position, remember the integration of velocity is going to give us position. And the way we represent position normally is an s of t. So the integration of v of t equals s of t. So if I integrate my velocity function, or 2t plus 1, now we're working in the variable of t, that's going to give me the original function s of t. Going ahead and integrating this, we end up with a t squared plus t plus c. And that gives me my original function. But I know that after 3 seconds, I was 20 feet away. So this really is an initial value problem where we give you the point 320. So if I plug in my position, which is 20, after 3 seconds, I know what the constant value now is going to be. So I know that 20 is going to equal 9 plus 3 plus c. 20 will equal 12 plus c, or 8 will equal c. So my original function, s of t, is going to equal t squared plus t plus 8. Now I can go ahead and actually solve my problem. I know my problem was where is the car after 10 seconds. So I can plug in and find s of 10. So I've got 10 squared plus 10 plus 8, or 100 plus 18, or 118. And this tells me that after 10 seconds, I will be 118 feet from my starting point. In example 2, we can get a little more involved with our problem because we can find a lot more things with it. So here we have a ballast. And a lot of people think, what is a ballast? Think of it as just a bag of sand. So we drop this ballast from a stationary hot air balloon that is at an altitude of 500 feet. The velocity of the ballast from after t seconds is negative 32t. That hopefully should ring a bell from when we were doing derivatives and we were finding the velocity of things falling off of a building. Remember the hammer or the coin problem? We found that it was falling at a velocity of negative 32 feet per second. Likewise, we knew that the acceleration was negative 32 feet per second squared. So back to the problem, can we find the height after the ballast is after any time t? And we can, because again, we're given the velocity. If I give the velocity, I can find the position by doing an integration. So I integrate negative 32t dt. Integrating this gives us s of t is going to equal negative 32t squared divided by 2 plus c. And negative 32 divided by 2 gives me negative 16 t squared plus c. And that's my s of t, which that should look familiar to us, again, from our problems that we did back before with the hammer falling off of a building. We can go ahead and find that c value now because we know that a hot air balloon was at an altitude of 500 feet when it first started falling. So I know that I was at 500 feet when my time was 0. Or I can come up here and give him the point of 0, 500. And a lot of times we're going to see that that 0 is going to be very important because that's our initial information. So I know that 500 is going to equal c. So my position, s of t, is going to equal negative 16t squared plus 500. So now the question is, well, when will the ballast strike the ground? Well, I know the position at any given time is negative 16t squared plus 500. What do I know about the height when the ballast strikes the ground? I know the height will be 0. So 0 is going to equal negative 16t squared plus 500. Now I can go ahead and solve for t. I can go ahead and subtract my 500. That equals negative 16t squared divided by negative 16. Throw that into my calculator. So I have negative 500 divided by negative 16 gives me 31.25. And that gives me t squared. To get t by itself, I'm going to take the square root. So I'll take the square root of 31.25. And that gives me approximately, after 5.590 seconds. Remember, when we take the square root, we get the plus or minus. But in this case, we're working with time. Time's not going to be negative, so we're only working with that positive value. So can we find the velocity then in part C of the ballast when it hits the ground? Well, I know it hits the ground at about 5.59 seconds. I also know the velocity at any given time is negative 32t. So if my velocity at any given time is negative 32t, I can find the velocity at 5.59 of a second. So that gives me negative 32 times my 5.59. Again, if I use my stored value in the calculator, I get a more precise answer. Negative 32 times my answer gives me a velocity at negative 178.885 feet per second. And those are a couple of types of word problems that we're going to see and we'll be working with over the next couple of days.